Hey, in this tutorial we're going to be looking at inverse trigonometric functions. So you need to remember that for an inverse function to exist, the original function must be a one-to-one function. So if we look at the sine function here, they were just drawn pretty roughly, you can see that it is clearly not a one-to-one function, okay, because it doesn't pass the vertical and horizontal line test. But what we can do is just take a region of the graph, okay, that is one-to-one. So a common one is from negative pi on 2 to pi on 2. Okay, we could go a smaller, that's like our maximum sort of size of our domain that we can use. Of course you could use something much smaller, okay, a small region there, or you could just move across and use from pi on 2 to 3 pi on 2 down there and use this region in here. Doesn't really matter too much, but the idea is that we have to use a smaller domain, okay, in which the function is one-to-one. So we'll stick with using the minus pi on 2 to pi on 2. Okay, so we'll look at using that function. Okay, so then when we're looking at that, okay, we can see that it is now one-to-one. Okay, so it's this purple region here is our one-to-one region. Okay, and so our inverse, okay, will then, I'll better switch colours again. Okay, when we do our inverse, okay, instead of going up and down from -1 to 1, well, that's now going to be our domain. Right, and we're going to be up to pi on 2 and down to minus pi on 2. Right, and our graph will look something like this. Okay, with closed dots because we're including our endpoints. Okay, so remember when we take our inverse, we switch our domain and range, and therefore we switch our x and y values. Okay, so it looks something like that. Okay, our general results of the inverse for sine is that if we have our function, okay, that is defined as from -1 to 1, going to negative pi on 2 to pi on 2, okay, then that is how we define our inverse. Okay, so we write it as sine to the power of -1. Okay, an alternative way is writing it as arc sine. Okay, but usually it's easier just to write sine to the power of -1. Okay, so that's our full definition of this function here. Okay, if we were to take sine of the inverse sine of x, okay, well that equals x if x is an element from -1 to 1. Okay, or we can say if we take the inverse of sine of x, well that will equal x if x is an element of minus pi on 2 to pi on 2. Okay, so they're our general results that we get from our inverse sine functions. Okay, so what we can do is there's a example we'll just have a quick look at. Okay, so we've got find each of the following: the inverse sine of 2, the inverse sine of 5 pi on 6. And our last one is sine of the inverse sine of 0.5. Okay, so when we look at that, okay, well, we're saying that x is equal to, this is our first one, inverse sine of 2. So that's saying that sine of x has to equal 2. Okay, and we know that sine never goes above 1. So therefore that does not exist. Okay, so the first one's nice and easy because it doesn't exist. Okay, our next one we need to look at this and go, okay, well when does sine equal 5 pi on 6? Okay, and we know that sine equals sine of 5 pi on 6 is equal to a half. Okay, it's in our second quadrant. Okay, and then that means that we go, okay, well then we're saying that the inverse sine of this part, which you know equals a half. Okay, and we go, well, since we're in our since we're looking at being in here, okay, we only have one solution. Okay, because in here we've got to be in our domain negative pi on 2 to pi on 2. We've got to be in that domain. Okay, so there's only one solution to that, and it is pi on 6. Okay, which is our basic angle for up here anyway, which makes sense. Okay, when we're looking at our last one, okay, here, okay, well that one is simply 0.5. Okay, because basically we're in our right domain of negative 1 to 1. Okay, and if we take the inverse of that, okay, we'll get a value. Okay, which then when we take the sine of it, we just get back to that same value. Okay, so it's not much work at all for that one. It's just to state the result. Okay, now we can start having a look at our inverse cos function. Inverse cosine function. Okay, and in a similar way, okay, we should all be pretty comfortable with what the cos graph looks like. Looks something like that, and again we get in trouble when we start trying to find the inverse function, because it won't be a function, okay, unless we restrict the domain. Now the usual restriction we do for this one is by going from 0 to pi. Okay, we go for that function, that domain, from 0 to pi. Okay, it's the largest restriction we can have. Okay, again, we could have smaller ones, but you wouldn't really bother. Okay, so when we do that, okay, then again, we're looking here, well, in this part here, well, we're still going from negative 1 to positive 1, negative 1 to positive 1, so they now become our that was our range, sorry, so it becomes our domain. So we go from negative 1 to positive 1. Okay, and we were from 0 up to pi, so that's for our domain, so that's now our range. To pi, and so when we sketch that, okay, we end up getting a function that looks like this. Again, we're including our endpoints. Okay, we include our endpoints. So our general results that we get is that our inverse cos function can be defined by our domain from negative 1 to 1, okay, with a range of 0 to pi, okay, and f of x equals the inverse cos function. Okay, so that's how we define our cos function. Okay, and again, if we look at taking cos or the inverse cos of x, well, that equals x if x is an element of negative 1 to 1. Okay, and if we take the inverse cos of cos, that equals x when we're in the domain of 0 to pi. Okay, and that's all we need to do. Okay, so what we will look at is a couple of worked examples like the ones for sine. So we say, okay, well, if we want to find each of the following, so we've got the inverse of cos of 3 on 2. Okay, the inverse cos of 5 pi on 4. And we have cos of the inverse of cos of pi on 12. Okay, again for this one it's very similar to our sine one. Okay, it doesn't exist. Okay, this one does not exist because if we say x equals inverse cos of 3 on 2, well then cos of x equals 3 on 2, and we never have a value bigger than 1 for our sine and cos values. Okay, so it's very similar. Okay, for this one we've got to approach it the same way as we did for sine. We need to go, well, what is cos of pi on 4? Okay, and because we are in the second quadrant, no we're not, we're in the third quadrant, okay, cos is negative, and cos of pi on 4 is root 2 on 2. So here, our cos of 5 pi on 4 is equal to root 2 on 2, but we're in the third quadrant, so it becomes negative. Okay, so then we're going, well, inverse cos of negative root 2 on 2. Okay, there is only one solution for when that happens. Okay, and that's going to be, and this is in our domain of 0 to pi on, from 0 to pi. Okay, and it's going to happen at 3 pi on 4. Now that's because, okay, really how we get this is we say, well, we're 5 pi on 4, that's in the third quadrant. We find our value in the third quadrant by going pi plus theta. Okay, so it's going to be pi on 4 is going to be theta, our basic angle. Okay, so again when we look here, okay, well, and the only time this is going to work for the domain of 0 to pi, right, is if we're in the second quadrant, and the second quadrant is found, our angle is found by going pi minus theta, and we know that theta value is pi on 4, hence we get our answer 3 pi on 4. Okay, and again for this one, nice and easy, because we're cos of our inverse of cos, it is just straight up our value. Okay, the cos and inverse cos just cancel each other out, leaving us with our value. Okay, so we need to look at our double angle formulas. Okay, so we've used our double angle formulas before, but we can have to use them in these type of questions as well. So we want to find the exact value of sine of 2 inverse cos of 2 on 5. Okay, so what we're doing is we're saying, okay, let's just say theta equals what we've got our inverse cos. So we're going to say that okay, is what we've got, our inverse cos of 2 on 5. Okay, so that means that cos of theta, okay, is going to be 2 on 5. Okay, so we're saying that we've got a triangle then set up like that. Okay, so then we need to find this side of our triangle, which will be square root of 5 squared take 2 squared, which will equal the square root of 21. That's our side length to our triangle there. Okay, so then really we're saying, okay, that theta is here, so we're saying sine of 2 theta, okay, and we know that's equal to 2 sine theta cos theta. Okay, well we know sine theta is our opposite over our hypotenuse, so we say it's root 21 over 5 times cos of theta we know was 2 on 5. Sorry, should be in times there. Okay, and we put all that together and we end up with 4 root 21 on 25, okay, as our answer. So what we've done is we've let theta equal this bit in here, okay, so that we knew what cos of our angle had to equal, so we could set up our right angle triangle, okay, find our unknown side, okay, and then use our double angle formula, because this, of course, when we did this substitution, became sine of 2 theta, because we said this part here is equal to theta. Okay, so we just need to have a look at our inverse tan functions to finish off. Okay, so remember, our tan function is our one that's a little bit different. Okay, so we've got asymptotes for our function, and clearly we don't have a one-to-one function again because it doesn't pass the horizontal line test. A nice easy restriction though is just between our asymptotes. Okay, works out well. Okay, however, this time instead of using square brackets, we've got to use round brackets for our domain because we've got asymptotes. Okay, at our domain, at the end of our domain are actually asymptotes, so we've got to use round brackets so we don't include them. Okay, so what happens then is we say, well, we can define our function as f is all real numbers because our range was all real numbers, that becomes our domain. We know our range now is minus pi on 2 to pi on 2. Okay. F of x equals inverse tan of x. Okay, so that's how we're defining our function this time. Okay, our inverse function. So when we do that and we actually graph it, well, we're just looking at graphing part of it here. Okay, so this time we've got minus pi on 2 up to pi on 2, and these are now horizontal asymptotes. They were vertical asymptotes before, but now they become horizontal asymptotes. Right, and our graph looks something like that. Okay. So we'll have a look at. Oh, sorry, we haven't done our general results either, have we? So that's our equation. Okay, but we also say that tan of the inverse of tan of x equals x if x is an element of all real numbers, okay, and that the inverse tan of tan of x equals x if x is an element of negative pi on 2 to pi on 2. Okay. So we'll have a quick look at a worked example. Okay, so we've got inverse tan of 11 pi on 6, and we also have tan of the inverse tan of 2. Okay. So for this one, okay, we're looking at tan of pi on 6 to start off with. Okay, well, you think 11 pi on 6 is in the fourth quadrant. We find our angle in the fourth quadrant by going 2 pi, take our angle, okay, and that's going to equal 11 pi on 6. So our angle is equal to pi on 6, okay, and tan of pi on 6 is root 3 on 3. However, we're in the fourth quadrant where tan is negative. Okay, so then we're going the inverse tan of negative root 3 on 3. Okay, and for that one, well, we've got to be where x is an element of negative pi on 2 to pi on 2. Okay, that's the one that we're going to be using. Okay, so there's only one solution for that one, okay, which is going to be where x is equal to negative pi on 6. Okay, it's the only time that we're going to be able to get that. Okay, which is basically the equivalent to our answer here. Okay, of our 11 pi on 6. Okay, and our second one over here, okay, it's straight up same as the other ones. We just need to state our answer of 2 with what's in the brackets. Okay, so we can also use our compound angle formulas for these. In these, okay, we've got 2 more work examples to go. So we use our compound angle formulas. So we're saying that we've got cos of the inverse sine of 12 on 13 minus inverse tan of 3 on 4. Okay, we want to evaluate that. Okay, so we're going to let A equal this first bit, and let B equal our second bit, our inverse tan of 3 on 4. Okay, that means that sine of A, okay, so if we actually work with this, sine of A equals 12 on 13, okay, and tan of B equals 3 on 4. Okay, so we can set up a couple of triangles here based off this one. Okay, we've got angle A there, well we've got 12 and we've got 13. Okay, so we need to work out our other side, okay, which will be square root of 13 squared take 12 squared, which is square root of 25, so it's 5. Okay, and we've got to set up a triangle for this one. Which is 3 and 4, so we know that we've got to be, this is B, we've got to be 5. Okay, a 3, 4, 5 triangle. Okay, so that means, okay, so we're getting there here. So what we need to find now though is we've got sine of A. Okay, so I might just start doing a bit of a list of what we've got. You know, sine of A is equal to 12 on 13. Okay, we need cos of A, okay, which is going to be 5 on 13. Okay, we need sine of B, it's going to be our 3 on 5. We need cos of B, which is going to be 4 on 5. Right, now we've got everything that we need to actually work on this. So, by doing this substitution, what do we turn this into? Well, that became cos of A minus B. Okay, and we know that that is equal to cos of A cos of B plus sine of A sine of B. Okay, and so we can simply sub in all our values. So cos of A, 5 on 13, cos of B, 4 on 5, okay, plus sine of A, 12 on 13, times sine of B, which is 3 on 5. Okay, so we've got everything that we need there, and when we simplify that, take my word on it, we end up getting 56 on 65. Okay, so almost there. We just need to look at one last section, okay, which is determining the maximum domains and ranges. Okay, so for y equals the inverse sine of x, okay, the domain is our -1 to 1, our range is from minus pi on 2 to pi on 2. So this is just summarising some of what we had earlier. And if we have y equals inverse cos of x, okay, our domain is again negative 1 to 1, okay, and our range, okay, is from 0 to pi, okay, and for y equals inverse tan of x, domain is r, all real numbers, and our range was for negative pi on 2 to pi on 2. So for our inverse trig functions that have been dilated or translated, we can apply these dilations and translations to determine the domain and range of the transform functions. So we'll just do one last worked example, which is state the domain and range of y equals 2 inverse cos of 3x take 2 on 5 take 3. Okay. So remember that our domain for this, okay, is negative 1 to 1. Okay. So we need to think, okay, well, modulus of this part, our 3x take 2 over 5. Okay, well, that's got to be less than or equal to 1. Okay, or, I mean, the other way to say that is that we've got to be between 3x take 2 on 5. Sorry, that's positive 1. Has to be between minus 1 and 1. Okay, so we have minus 5. Is less than 3x take 2 is less than 5. Okay, we've got to take, we've got to add 2 to both ends, sorry. So we then have minus 3 to 7. Okay. So we're getting there with that. So for our domain, okay, we've got to divide by 3. So our domain, I'll change colours. Okay, we're going to divide by 3, so it's going to be from, sorry, and I lost my equals to on these signs by an accident. Going to be negative 1 to 7 on 3. Okay, we know our range is usually from 0 to pi. Okay, but we have a dilation by a factor of 3 parallel to the y-axis and a translation 2 units down parallel to the y-axis. So the range, okay, becomes, well, we've got to times that by 2, then we've got to take 3 away. Okay, so we end up with 2. Okay, so when we end up doing that, we find that we get, well, 2 times 0 is 0, take 3 is negative 3 to 2 pi minus 3, okay, which is an odd looking domain, but that's fine, that's the way it works sometimes. So our range ends up being that. Okay, so start off here, okay. We just looked at setting up an inequality for our domain, okay, and actually like multiplying through and add through and divide by 3 to get our domain, okay, through our all those translations. And then we looked at our range where we changed our amplitude, we multiplied by 2 and we took away 3, did that to our range here to get our final answer. So that was a particularly long video, but hopefully it's enough to get you through that section.